This is the fourth part of Lesson 25 in heat transfer. Lesson 25 focuses on the fundamentals of thermal radiation heat transfer. In the last lesson, we looked at the four physical processes associated with thermal radiation heat transfer between two surfaces. In this part of the lesson, we will describe a fundamental concept in thermal radiation heat transfer known as the black body surface. The black body surface is one of the most fundamental ideas, and it is important that you understand what a black body surface is and why it is so important in radiation heat transfer theory. By the end of this lesson, you should be able to explain in your own words the concept of a black body surface. You should be able to list from memory the three defining characteristics of a black body surface. And finally, you should be able to explain the two most important trends in the spectral emissive power from a black body surface. On with the lesson.
Okay, so emission is, I'd say, the more complicated of the most complicated of the four processes in terms of thinking through. And we need a way to talk about emission. And the way that we talk about emission is through this idea of what we call a black body surface. So a black body surface is a theoretical construct. It doesn't actually exist in nature. It kind of exists from the mathematics that has been developed to deal with radiation heat transfer. But the theoretical construct goes like this. A black body surface is one that has these three traits. One, black bodies emit the most radiation possible at any given temperature. No real surface emits more energy than this imaginary black surface does. It's the upper limit, right? It sets the upper bound for what can be emitted. Two, black body surfaces absorb all incident radiation. So think in terms of the properties. If the black body surface absorbs all incident radiation, what's true about tau for a black body surface? It's got to be 0. What's true about rho for a black body surface? It's got to be 0. So then what must be true about alpha for a black body surface? It's 1. Okay, so any surface in which the absorptivity is 1, that is by definition a black body surface. Okay. And you're going to see a little later that to emit the most radiation at any temperature, the property emissivity will have to equal 1, 2. So if you want to make a note of that. So the emissivity of a black body surface is by definition 1. Okay, that sets the upper bound. And then the third characteristic of a black surface is that it emits diffusely, which means that it emits energy equally in all directions. So there are really two complicating factors for radiation heat transfer in comparison to convection and conduction. One is radiation depends on the wavelength. So we have to deal with this wavelength dependence. Right, the photons all have different energy levels, and surfaces emit a spectrum of photons. They're not all the same photons. They're a bunch of different energy levels. That's tricky. So radiation depends on the wavelength of the radiation. The other, radiation is very much directional. Right, like radiation can stream off in this direction. Radiation can also be streaming in this direction or this direction. In fact, it can stream in all 300, all directions possible. So whereas in, say, conduction, we had the possibility for independent variables of there being time in 3 spatial coordinates, right? T, X, Y, and Z. That's certainly true for radiation, but now radiation also has 2 directional coordinates, right? An azimuthal angle and a elevation angle, and it has wavelength as a dependence. So there are 7 possible independent variables that can control radiation. So it makes it more complicated. One of them is the directional dependence, and this just means we go in all directions equally, just like the little picture shows. Make sense? So not all real surfaces, some surfaces actually emit preferentially in one particular direction over others. Not black body surfaces though, they emit equally in all directions. So emission from black body surfaces was the subject of much research for a long time, especially in the like 1810-ish to 1910-ish range. Okay, and we as I say civilization, human civilization, we've been aware of radiation for a long time, and we had a couple of different scientists come up with models for predicting radiative emission. Planck came up with these sets of curves for how a black body emits radiation. These curves show you how that happens as a function of temperature and of wavelength. So wavelength is on the x-axis, and you have different curves for different temperature. And what's on the y-axis is the radiative power, the emissive power. It's called the spectral emissive power. So it's the watt per square meter at a particular value of the wavelength. It's like if the surface has a temperature of 1000 Kelvin, it's emitting at 3 micrometers, 10 to the 4 watt per square meter in that particular small wavelength band around 3 micrometers. Makes sense? That's what this is showing. It's the distribution of energy being emitted from a surface over the wavelength spectrum. And there were 2 important observations to make about Planck's distribution, which is given by this complicated equation up here. And that is that, one, if you look at the curves as a function of temperature, as the temperature increases, right, the area under the curve increases. And we're gonna, on the next slide, I'm gonna show you that there is, we can predict that, we can actually calculate that. Right? But just know that the higher the temperature, the more energy comes out, or the rate at which energy comes out goes up. The higher the temperature, the faster the energy comes out. And then the other thing to note here is that as the temperature goes up, right, there is a peak in the Planck distribution, and the peak shifts to lower wavelengths. You see that? Like it shifts to the left, like the peak is moving. You can actually draw a line through all of the peaks, and it would look something kind of like that. Right? That's like, we call it the locus of maximum. And there is a way to predict, right, the wavelength at which the peak occurs. And it's from something called Wien's displacement law. So this is a German name. In the German language, the W takes on the sound. It's like a V almost in English. So this is Wien's displacement law. And Wien's displacement law allows us to predict that the wavelength at which that maximum occurs, 2897.6. Okay, so the product of the temperature of the surface, T, the wavelength at which the maximum occurs, and this thing, N, this is called the index of refraction. You may have seen this in physics. It shows up in optics a lot. Right? It takes on a value of 1 for air or a vacuum. And then, you know, different media get different numbers, but for example, glass is usually around 1.4. So that's the index of refraction it's the index of refraction of the media into which the energy is being emitted. So like for glass, if you imagine like the interface of the glass, right? If you're emitting energy into the glass, and the N is equal to 1.4. I don't want you to forget that's there though, because I spent about a week of my life trying to debug a code, and it turns out that I forgot to put the N in. So that was really frustrating. So please don't forget the N. So for example, we could calculate, if I told you that the effective temperature of the sun is 5,777 Kelvin, right? Which is why this yellow line is yellow. It's supposed to represent sunlight. we can figure out where that peak is, right, by using Wien's displacement law. So if we're emitting into air, n is equal to 1, so then the maximum lambda is equal to this 2897.6 micrometer Kelvin. You divide by T, 5,777 Kelvin, and that lambda max is about 0.5, right? So 0.5 micrometers. So if we come over and we look at the spectralness of power, so here's 0.1, 0.2, 0.3, 0.4, 0.5. 0.5 is right here. So I like this graph because it puts in the rainbow there. So that's right on the edge of green. So sunlight emits the most of its energy in the green light band. So that's the color that you see a lot of outside. Yeah. I don't think that's necessarily a coincidence. So this is green. What we usually ascribe to green. Okay, so that's Wien's displacement law. That gives us this peak, right? And so what's important for me that you know is that as you heat things up, right, you're shifting that peak emission to the left, which is also why when you heat things up, it starts to look red, right? Because the peak is getting shifted into this part of the spectrum where we can see. So when you heat things up, right, our eyes are most sensitive to the top part of the curve, right? Wherever that peak hits, that's where we start to see. So that's why things start to look red first. And as you heat them up more and more and more, they start to look more and more white because you get more and more of all of the colors coming together, right, to give you white light. When you put them all together, you get white.